Hello everyone, welcome back to my channel, The Data Odyssey. If you're new here, we dive into the world of data and actually make it easy to understand. In the last video, we discussed the limitations of Hive tables, things like manual partitioning, right? And then we had issues with inconsistent snapshots, correct? And then we also had the issue of schema evolution, correct? Now, I also told you that Apache Iceberg is the table format which tries to solve all these problems, and that also with better performance, and maybe I can say good performance, or the best performance amongst all the table formats. Okay, and these problems are actually solved by Apache Iceberg. For example, the problem with partitioning, it's solved using hidden partitioning, right? I've mentioned that in the last video. Okay, and then it tries to solve the problem of snapshots using means by storing snapshots, basically by addressing the issue of storing version history, right? So it does store the version history, and that also consistently, basically, so consistent snapshots actually. Okay, and then for schema evolution, it actually offers seamless schema evolution. All right, so these are the three major issues that Hive had, and actually Iceberg as a table format tried to resolve. All right, but how does Apache Iceberg as a table format try to make this work behind the scenes, right? This is a big question that we should have. Obviously, I told you about the entire Hive table issue in my last video, and then I also explained, or maybe just mentioned, 1,000 feet overview of how Iceberg tries to resolve it. But you must be having a question that, okay, it does try to resolve all the issues with Hive, but how does it do it? For that thing, we need to deep dive into the world of Apache Iceberg's architecture, basically. Okay, and that's what we are diving today into, the architecture of Apache Iceberg. Now, before starting with the architecture, let me just break you down the architecture into three simple things. Okay, at a high level, just like let me just give you a 1,000 feet overview of what is exactly in this architecture prior to starting up with it. Okay, but prior to even that, let me just show you the architecture so that you get happy, right? So this is the architecture of Apache Iceberg table. Okay, now, before looking at this image, just listen to me that what I'm trying to explain. Okay, at a high level, Apache Iceberg's architecture is designed to handle large scale data that we have known in the last video while maintaining strong consistency and performance. And it does achieve it with the help of three layers within its architecture. Okay, it organizes just the data basically into multiple layers. All right, and these multiple layers include three parts to it, or three layers to it. The first layer, you can say, is the um, data layer, which is the most important, you can say, amongst all of them, because first of all we need data to actually see it through the table. First of all, data should be there. Then we have the metadata level, which is the second most important part of the Apache Iceberg table format. And then we have the catalog layer. Okay, now of course I'll explain you the importance of each of these layers in an in-depth manner, but just a quick overview of how these individual layers basically work. Okay, now, the data layer is the one which actually stores the actual data, and uh, there is another thing which it also does store, but I will not tell you at this point. Maybe towards the end of this video. Okay, and then there's the metadata layer, and it tracks the data. That's what we should know. So this actually tracks the data. This actually stores the data. Okay, and then there's the catalog layer. Okay, and what does catalog layer do? It actually helps to track the table states. So track table states. Now, what do I mean by table states? That also we will get to know. But just keep these three things in mind. So data layer tracks the data, metadata layer, data layer actually stores the data, metadata layer actually tracks the data, and then there's the catalog layer which tracks the table states. So maybe you can say that it tracks the tables. Okay, so these are the three things that we have in our Apache Iceberg architecture. All right, but right now then let's start to deep dive into each of these individual layers. Okay, so first of all, whenever you query upon a particular table in simple SQL, okay, what we do, we have three parts to it. First of all, we have the catalog to it, right? So I'm just trying to tell you the basic thing that does happen. Or if and if you're not clear, or you're new to this world of data, then this is something new for you, or it's better to just revise the concept, right? So we have the catalog layer. Then after that, we have the schema within which the table is present. And then we have the table itself. Okay. And beneath this table, we have got the data, right? And we get to see the data through the lens of a table, correct? So we have the catalog, which is actually the godfather, right? And then the godfather has got its children, which is the schema. And then these children have got their own children, which is the table, right? Okay, so this is actually the entire way to access any table, correct? So I just wanted to introduce you this part, but like we'll get to know that why I told you. Okay, so first of all, at the bottommost part of the Apache Iceberg architecture, you can see we have the data layer, right? Now what is this data layer basically? So this data layer has got the data files, okay, and these are the files where your actual data is getting stored. Okay, so these are the files where your actual table data is actually getting stored. Now I've told you in the OLAP architecture video, I'll just put that anywhere above. You can see that in the OLAP architecture video I've told you what is a file format basically, right? It's the way in which the data is getting packaged, you can consider, or with an analogy to a supermarket, it's the way different products are getting packaged. A bottle of oil may be packaged as a can. It may be packaged as a plastic bottle. It may be packaged in the form of plastics, right? So different forms of packaging for same data. Similarly, file format is for the same product actually, right? So similarly, file format is something which actually packages the data in different format according to your requirement, according to your needs, right? And so data is getting stored in this data layer in the different file formats that we desire, right? And what are the different file formats that we have got the Parquet file format, right? We have got the ORC file format, we have got the Avro file format, and actually these can be actually classified or reclassified into two main categories. One is row file format, and then we have the columnar file format, right? So these are the two ways in which we can classify our files, correct? So this means what Iceberg can do it can directly access the specific file it needs. Okay, but how does it actually access it? That's what we also need to know. Okay, so we have got the data files, right? Now, in my last video, while explaining the Hive issues, basically, I talked about partitioning concept. Okay, if you have not gone to the last video, you must see it because it's very important. That's why I put up this video on my Apache Iceberg series, right? I explained to you about the partitioning concept, how a bigger chunk of data is further classified or restructured into smaller chunk of data across the many data files, right? But I also mentioned that Hive follows a directive based architecture. And what is does, like upon the basis of the columns that you partition, it actually partitions the data into multiple chunks on the basis of the unique or distinct values within that partitioning column, right? Now suppose you have got a particular record to get, okay, and um, like, but you are querying on that particular thing, on a particular column which is not partitioned, okay. So what will Hive do? It will scan the entire partition, right? We have partitioned on a particular column, but you are searching on a different column. What will Hive do? It will scan the entire partition, right? But a partition has got multiple files within it, correct? So that means it will scan the multiple files, okay, and that's the issue what Iceberg tries to resolve. What Iceberg does is it tracks the data at file level rather than at partition level. So Hive actually tracks data at partition level, right? And the partition might have multiple files, correct? That means it is scanning larger number of files, okay. So let me just write it down, multiple files, right? But what Iceberg does, it tracks the data at file level. That means lesser number of data to scan, and this means a huge improvement over Hive, where partition level tracking basically often leads to slower queries and complex maintenance, all right. So that's one of the first thing that we have got to learn, in which Iceberg actually tries to work. So it accesses these data files at file level rather than partition level, and that's a huge improvement over Hive, okay. So we have got to know that how Iceberg tries to resolve one of the issues with Hive actually, right? So we have gone through the first part, but there's another sub part to this first part actually that I wanted to explain, okay. So while explaining this data layer, I was going to mention another thing called delete files. Now, what is the delete file basically? So this data layer not only has got the data files, but it has also got the delete files. Now, what do I mean by this delete file basically? Okay, so along with data files, we also have the delete files, and these are actually used to track the row level deletions without rewriting the entire data. So row level deletions are tracked. Now, how does it improve performance? So it tracks the data that is deleted actually, okay. But rather than deleting from the actual data file, it tracks it in a different file. The actual data file remains the same, no data gets deleted from it, but the records that you want to actually delete, it is actually stored in this delete files, okay. And when the user actually queries upon that data after the delete operation, basically what happens is that rather than, so the engine works in such a manner that it will not show user those records which are present in the delete file, okay. So it combines both the data file and the delete file whenever the user actually queries the data. So whichever records are present in this delete file, okay, whichever records the user has instructed to delete is tracked in these delete files, and whenever user queries on the table to look at the records, he or she will not be able to find those records which are actually deleted, because the engine doesn't show this record which are present in the data files, okay. So these set of records which are present in the delete file will actually be shown to the user in such a manner that the data which the individual has deleted is not visible, but it's actually present in the data file, all right. So for, like, if we got confused at this point, so suppose example you have 1 2 3 4, okay, you have these four records in your data file, and suppose user instructs to delete record 4. What will happen? The data file will remain intact. 1 2 3 4 will be there within this data file, all right. But the delete file will get an input that record 4 is going to be deleted. So when user queries upon that particular table, what happens? These two data file and the delete files get combined together, and it tries to, not show fourth number record to the user, okay, even though it's present in the data file, and it will show only 1 2 3. So maybe you can say it's kind of bluffing that it tries to do basically to reduce the dependence, or reduce the the pressure on the data file. You can consider it in that manner. Okay, it distributes the task according to the way the process can be made faster. Okay, so this file based tracking basically is one of the key reasons why Iceberg is so efficient compared to Hive. Okay, so this is the first layer to the Apache Iceberg architecture. Okay, now the second layer is the metadata layer, and this is, you know, also one of the most important layers within the Apache Iceberg table. Okay, so we have the metadata layer over here, and what does it mean by the metadata layer? Basically, like, what does it do? Basically, it keeps tracks of what's happening in the data layer. Okay, so tracks all events in data layer. Okay, so the metadata layer includes three parts to it again. Okay, at the bottommost part you can see the manifest files. Okay, then above it you can see the manifest list, and then above it you have got the metadata files. Okay, so let us follow a top to bottom approach so that it's easier to understand. Okay, so this metadata file, what it is. So metadata file stores details about the table schemas. That's why I was explaining you this part. Okay, so you maybe like just consider this thing. Like I told you over here, right? We have got the catalog, we have got the schema, and then we have got the table. Okay, but why I told you this part? Okay, because we need to understand what is schema, we need to understand what is a catalog, and of course we know what is a table, right? It has got the data. It's through the table's lens that get to see the data. Okay, but behind this in there are multiple, we actually see the files that we have. Correct. So the metadata file stores details about the table schema, the partition information, the snapshots, the current snapshot. Now, what is a current snapshot? What is that? We will, of course, know it. Current snapshot means the uh, current version of the data. Okay, so what is the current version of that particular table? This is tracked by the metadata file. Okay. So every time a change is made to an iceberg table, a new metadata file is created automatically. Okay. Via the catalog. And this ensures that we get to know which is the most recent version of that particular data or the table. Okay, and then there's another thing also. So like, we get to know that when multiple writers are writing to a single table, so when writer 1 writes to that particular table, we get the version 1. Then when writer 2 writes to the particular table, we get the version 2. Now when these two are writing at the same time, what it does, this version actually helps us track that if writer 1 has got the entire data written, and the version history has been updated to version 1, only after that the writer 2 will be allowed to update. Okay, so it helps to avoid any conflict in this situation where both the writers will be writing at the same time to the same partition. Okay, so like if this issue occurs, it will raise an error or an issue. And what you can see on the screen over here, we have got the metadata file, you can say A, and we have got the metadata file B. Now you can see a finger over here. Why I've put this up on the diagram. So A file has got the zeroth snapshot. Okay, so the first version of the data. Okay, then the B file has got this zeroth snapshot. That means the zeroth or the first version of the data, and it also has got the first snapshot. So these are the snapshots basically. Okay, so zeroth snapshot has got the first version of the data, one snapshot has got the second version of the data, and the metadata file has got the information that which is the what is the current snapshot of that particular table. Okay, and the current snapshot is one actually. Okay, all right. And why, how do we utilize it? Basically, we'll when we query upon that particular table, what we expect the most recent version of the table, right? And how do we get to see the most recent version? It's through this metadata file actually, which tracks that which is the most recent version of the table. So it knows that one is the most recent version of the table. Okay, so this helps us ensure the entire history of the table. All right. So this is the first thing. Okay. Now then we have got the manifest files. Okay. Like maybe prior to that, then we have got the manifest list actually. Okay. Now what are this manifest list? Manifest list is essentially the snapshot of the table at a given point of time. Okay. What it does, it see, metadata file A has got a manifest list. Metadata file B has also got a manifest list. So individual metadata files have got their own set of manifest lists. Okay. Now, what is present below this manifest list is the manifest file. Now, what you can see over here, a single manifest list has got multiple manifest files to track, right? So this particular manifest list has got this file, has got this file and this file. So all the three manifest list files are getting tracked by this manifest list. Basically that's what you can understand from the diagram. Okay. But what does it mean actually? So prior to understanding the manifest lists, let us understand the manifest files. So manifest files, you can see we understood what are the data files, right? But what does manifest file actually do? So the manifest files tracks the actual data files. So the one above the data files is the one which tracks the data files. Okay, that's what you can understand. So it tracks the actual data files. So it tracks data files. Okay. And these manifest files actually store what kind of information about data files, like what kind of tracking does it do? They store details like column statistics, record counts, partition, partition details. Okay. So this actually allows the iceberg to prune unnecessary files. That's what I told you, right? So it doesn't scan all the records, it scans only the relevant data, all the files, it scans only the relevant files. And how is it able to scan those relevant data files only? It's because of this manifest files, because it knows that which data file has got what kind of information. It knows the maximum, you know like maximum value in that particular partition. It knows the minimum value in that particular partition. It knows the record count in that particular table, in that particular data file, like each and everything. So it accordingly scans, like if we have got four data files over here, which data file to access. Like on the basis of id, if you partition a particular table, it will not scan all the data files. Okay. It will scan only the data file which, in which the id falls in its range actually. Okay. So it tracks these kind of information. So it tracks the data files. It has got it tracks details like maximum value, tracks details like minimum value, it tracks details like record count. Okay. And a separate manifest file is altogether created for data files and delete files. All right. That, like I explained you about the data files, right? About the delete files, right? Now this is extract information. So separate manifest file is maintained for what? Delete files, delete and data files altogether, right? Now it tracks both of them. Okay. So this is what we need to know about the manifest files. And then that another thing to explain that I was forgetting actually. So these manifest files actually have got their own schema, even like where it wants to store. So these delete files and data files are actually stored in the manifest files which have got the same schema. Just kind of a piece of extra information that I wanted to tell all of you. Okay. And then finally we have the manifest list. What is a manifest list altogether? A manifest list is basically or essentially a snapshot of the table at a given point in time. So it tracks all the manifest files. Okay. Again, in the same way, a manifest file, similar to the situation where a manifest file tracks the data files, a manifest list tracks the multiple manifest files. Okay. That is the first thing. Second thing, this manifest list is actually in Avro format. Okay. Now, the task what manifest list is does, it tracks the manifest files first of all, and it's essentially a snapshot of the table at a given point in time. Okay, it's basically the current snapshot of the table at a given point in time. Why do I say this? Because if you see over here, snapshot 0 is over here, right? Now metadata file A is pointing to this manifest list, correct? But again we have got snapshot B over here of the particular table or the particular data, but still this particular manifest list is pointing to this snapshot. Okay, so it points to the current snap, it points to the different snapshots. So each snapshot has got its own manifest list. So snapshot 0 will be stored in both the metadata files, but this 0 is related to a single manifest list. Okay, and this one which actually has got blur over here is related to this manifest list altogether, right? So let me just maybe a different color, because so this one is actually related to this snapshot, like to this manifest list. So each snapshot has got its own manifest list. Okay, and then it again stores information with respect to each manifest file in the similar manner. A manifest file stores information with respect to a data file. All right, so maybe you have got a clear understanding of the metadata layer, which was the most extensive part of this architecture, and also the data layer, which was also very important, right? Finally, we have got the catalog layer. Now what does catalog layer do? The catalog layer is where all the table metadata is registered and managed. Okay, and why do I mention the table metadata is registered and managed? It's basically like you have got a class, you have got class 10th. Okay, and in class 10 you have got multiple sections A, B, C, D, correct? Now within this section you have got multiple students, right? As student A, student, say Ram, student Shyam. Then you have got section B, students with net, students with section C, students in section D. So each of these individual sections have got their students. Now let us consider that these students maybe is analogous to the data files. These sections is analogous to the the schema or the metadata layer which tracks everything. And then we have got the class 10th, which is which actually refers to all the students, or you can say with respect to the data world, with to all the data files. Okay, so the catalog layer is the, you can say, the most important part again, because it's where all the table metadata is registered. Okay, so table metadata is stored in this catalog file. All right, so Iceberg supports different types of catalog again. So there are again multiple variations to the catalog that we can utilize according to our requirements. Again, even though we are not liking the Hive table, we can utilize its catalog, so we have got the Hive Metastore, which is one of the catalogs. Now each of these catalogs has got their own advantages and disadvantages, and we need to utilize it according to our requirement, according to the benefits that it offers. Then we have got the Hadoop catalog, or you can say the AWS Glue catalog. Okay, and then there's others, like there is Nessie catalog we have. It's open source project that we have. And yeah, so there are multiple catalog types that we, catalog companies that you can say we have altogether, or the types that we have. And these catalogs, what, how does it help? You can see I'm writing over here, it has got the current metadata pointer. So the catalog keep tracks of the current metadata file. Okay, this metadata file keep tracks of all the files, all these snapshot, and which is the latest metadata file, which has all the snapshots starting from the start till end, is tracked by this particular catalog. This catalog then accesses the current snapshot, current metadata file, which has got all the snapshot till the current version, which has called all the snapshot till the most current version of the snapshot. And then we are able to see actually the most recent form of the data, right? So this is This catalog is actually the reason that we are able to see a consistent state at any point in time. Now, what do I mean by a consistent state? So I'll explain to you this scenario like what we had faced in our project. So if you say like we have a single table and you are writing to that table from multiple sources. Now, whenever source A is writing, then first of all its state should get updated to state 1 maybe, okay, and only after that state B should be allowed to write if you are writing to the same partition. And again, if there's different partitions, then it's another issue where each partition updates the state of, like each partition updates the states parallelly, okay, and then we get to see the final state. Okay, so we need to look at this in this manner. All right, so this iceberg is the one which maintains the most recent metadata file, or has got the most current metadata pointer actually. And this catalog is the reason, or you can say which helps us maintain the acid properties basically, properties like isolation, properties like consistency. It works so well in a high concurrency environment for the Apache Iceberg table. So we are able to perform parallel streaming upon a single piece of table, to a single piece of table from multiple sources, and that's because of this catalog which which actually maintains the state in a consistent manner at a particular point of time. Okay, so suppose if two processes try to update the same table at the same time, like this example I've shown, Icebergs ensures that only one of them succeeds, and after that the second one succeeds. And this one avoids conflicts and ensures data integrity actually. Otherwise, if two different writers write to the same partition, then you know what the scenario, it will be an entire mess, right? Okay, so this is the entire architecture of Apache Iceberg that I wanted all of you to see or look at, and maybe not much videos on YouTube, but there with respect to this architecture of Iceberg table. And again, there is a bonus to this in this video, bonus section in this video where I explain something very different. Maybe you will not find them everywhere. Okay, and we'll look to that thing on the next slide. It's a long video, I do agree, but again it's an interesting video and it's a very required video, to understand something very important. Okay, so what you see on the screen you might not understand, right? And I would tell you at this point of time, no need to understand altogether. But on the screen you can see this what's written over here at the bottommost part is the structure of a Puffin file. Okay, it's a bonus part. If you want to listen to this thing, do listen. If you don't want, that's also okay, because whatever was important I've explained it to you. Okay, what is a Puffin file basically? Okay, so Puffin files are something which are actually stored in Avro format. Okay, now why did I say Avro format? All right, so it actually holds advanced statistics and indexes with respect to data, and this helps improve performance of complex queries. So the most important part is this Puffin file is present within the Iceberg architecture, and this files actually helps to improve the performance of query. How does it help to improve the performance of query? That's I will just explain you this part in a very concise manner. So for example, you wanted to know how many unique orders were placed in last 30 days. What will you do? You will run a query, right? Like select star from this particular table A, B, or C, whatever, where you know date sub or date add from the current date to minus 30 days or 30 days, depending upon the function date add or date sub, right? But what will happen with that, like how does Puffin file improve the performance? That's how we will see, right? So without Puffin files, what would have happened? The query engine would have to read all the data for those 30 days, right? Whenever you run the query and do aggregation from scratch, which would take a quite a while, right? So from scratch everything would happen without Puffin files if no Puffin files are present. Okay, but if we have got the Puffin files, what will happen? Iceberg already has got the pre-computed statistics, right? And indexes correct, with respect to that data. And Puffin file has them, right? And then we have them in the manifest list also, you can say, manifest files also, you can say. So what it does, actually, what does Puffin file do is like, if the Puffin files are present, then this query performance would improve significantly. Okay, so the key difference between a manifest file, you can say, and a Puffin file is the manifest Puffin file actually stores statistics beyond what's available in regular metadata files. Okay, and it actually helps to handle high cardinality queries and improve query planning. And this is one of the advanced features, which was well thought of in Apache Iceberg architecture by the people of Netflix actually. But more information, you can see, it's one of the advanced features of Apache Iceberg information than metadata files for complex query. Okay, right? Because it was some pre-computed statistics, some more information which metadata files do not have. Okay, so that's a wrap on the entire Apache Iceberg's architecture. In the next video, we'll go even deeper and explore how these individual components work together to solve the issues we discussed in Hive. Of course, we have discussed a lot of it in this video, how it does to resolve those issues. Like the snapshot part, I told you it's stored by the metadata files, and then I told you about the partitioning part, like it does not have to access all the partitions, right? I think we missed one part, which is related to schema evolution. I'll try to explain you this part, but rest, like apart from that, maybe in the next video I will start with the practicals. Okay, where we see, like whenever we create a table and then when we ingest data to it, or have any update on like perform any update on the table, or any merge statement, whatever operations we do, how these files change, and at each point of time, like insert, then data like first of all creating of tables, then insert of table, like from stage 1 to stage 2 to and then the updation of data, how or what data files and format data for, like what metadata files are formed, which are removed, which are there, and what each file has, what kind of information each file has got. We'll get to see all of those things, right? And how does it individually um, like contribute to this entire Apache Iceberg, right? So, like, if you found this video helpful, make sure to like and subscribe so you don't miss out on the next one. And if you have any questions or any thoughts, just drop them in the comments. I would love to hear from you people, and see you in the next one. Please do share the video.